Moving on, we can introduce the concept of center of mass. We recall weight is just mass times the gravitational acceleration. That is, if we divide our weight by gravity, we are left with mass, and mass is equal to the integral with respect to our differential mass. Thus, if we take our first moments of weight and divide by our gravitational acceleration, we are left with our first moments of mass. Our first moments of mass are expressed as follows. mx bar is equal to the integral of x dm, my bar is equal to the integral of y dm, and mz bar is equal to the integral of z dm. Now recall m is equal to the integral with respect to dm. Now if our gravitational field is constant, or our body force, i.e. an electromagnetic field, is constant, the location of our center of mass is going to be the same as our center of gravity. Let us consider a situation where we have a cylinder shown below, and we want to determine our center of mass. Now, our density varies linearly as a function of height. That is, rho z is equal to 200z. Now we're going to take the cylinder to be 1 meter tall and 1 meter in diameter. We are going to ignore significant digits for this problem. For us to determine our z location, we can take our moment about our x or y axis. We're going to take our moment about our y axis for this problem. And to do such, we need to look at the contribution of a differential volume some distance z above that y-axis. We can take a disk with a thickness dz. There's some distance z away from this y-axis, and this disk is going to have a differential volume given as a dz. The area of this disk is simply pi r squared. Therefore, our moment about our y-axis, m sub xy, is given as an integral with respect to m of z dm, which is equal to the integral with respect to volume of z rho dv. For our differential mass is simply equal to our density times our differential volume. This is going to be equal to integral from 0 to 1 z times the quantity 200z, which represents rho, and our differential volume is simply pi r squared dz. 200 and pi r squared are constant, so we remove those from our integrand, and we are left with 200 pi r squared times the integral from 0 to 1 of z squared dz. Thus, we'd have 200 times pi r squared times the quantity z cubed per 3 evaluated between 0 and 1, which is equal to 200 pi r squared per 3. Now we have to determine the volume of our cylinder, i.e. the denominator of our y bar equation. And we have the integral with respect to volume of rho dv, which is equal to the integral with respect to z of rho a dz. Recall, a times dz is equal to our differential volume. Thus we'd have the integral from 0 to 1 of the quantity 200z, which represents rho, times pi r squared, which represents a dz. This is 200 pi r squared times the integral from 0 to 1 of z dz, which is equal to 200 pi r squared per 2. Thus, the bar is going to be equal to integral with respect to v of rho z dv per the integral with respect to v of rho dv. And we have 200 times pi r squared per 3 within our numerator. We have 200 times pi r squared per 2 in our denominator. And we are left with a value of 2/3.